Right, so we're going to look at some properties of alkanes. As we know, alkanes only contain nonpolar carbon-carbon-carbon-hydrogen bonds, and they exhibit weak van der Waals forces, which affects their solubility and boiling point and melting points. So alkanes are soluble in organic solvents and not soluble in water because, again, they're relatively nonpolar, like dissolves like, and polar compounds are going to dissolve in polar solvents like water, and vice versa. Here's a table with some of the properties of alkanes, and you can see them compared, for instance, in boiling point, an alkane with 3 carbons compared to an aldehyde with 2 carbons. You can see as you put an oxygen atom inside the skeleton, you're making the compound more polar, and the boiling point and melting point are going to therefore increase. Why is that? Because to boil or melt something, you're going to have to break the forces in between the molecules that are holding them together. So you're trying to disrupt intermolecular forces. And that's easier to do if those forces are weaker to begin with. In other words, if you have compounds that are nonpolar rather than polar. So polar compounds are going to have stronger intermolecular forces to each other. And so boiling point and melting point also increases with molecular weight because of increased surface area. That also increases boiling and melting point. So as you get to larger and larger alkanes, the boiling points and melting points go up. And with isomers, that is when you have branching, boiling point is actually going to increase because you have compounds that are more sterically encumbered. That is, when you have branches, it's harder for the molecules to pack closely together, and therefore it's going to be easier to boil them or melt them. That is, to disrupt the intermolecular forces. Again, the branching makes it harder for the molecules to pack together and bind together, which makes it easier to boil or melt them. And with increased symmetry, typically melting point increases. That's kind of a minor concept. We'll come back to it at some point later in the year. Okay, so bottom line, alkanes not soluble in water because they're nonpolar. Alkanes are soluble in organic solvents because they're nonpolar. Okay, so very importantly, single bonds, that is, the bonds found in alkanes, carbon-carbon bonds, are rotating. They're constantly rotating. And so we're looking at rotation on this slide of the carbon-carbon bond. The two balls there, black carbon, the black balls are carbons, and we can see the effective rotation. You're moving that red substituent around somewhere else, and this keeps turning round and round pretty quickly. And there are there are an infinite number of conformations. That is, ways that the substituents on each of the carbons that are attached, where we're rotating the bond, there are an infinite number of ways that these can line up. And let's talk about some extreme ways, and that is where you have each of the hydrogens in this case all overlapped. That's called an eclipsed conformation, right? See, all the CH bonds are eclipsing each other, or you can overlay each of them. See that? They're all lined up on top of each other. If we rotate 60 degrees about this carbon-carbon bond, we get what we call a staggered conformation, where we're bisecting. Notice in the front, the CH bonds are bisecting the HCH bond angles in the back of the molecule. So eclipse conformation, staggered conformation. These are just two of an infinite number of conformations that we can get by rotation. It's a 60-degree rotation, obviously, to go from eclipse to staggered. Okay. So the concept of, or the term dihedral angle is one that we'll see over and over throughout your study of organic chemistry. And that's the angle that separates a bond on one atom from a bond on the adjacent atom. So when we have the eclipse conformation, we have a 0-degree dihedral angle. When we go into the staggered conformation, 60-degree rotation, not coincidentally, we have a 60-degree dihedral angle. Notice how that's figured. That's figured by the angle that separates the bond on one atom from a bond on the adjacent atom. 60 degrees between the CH bond and this rear CH bond. I want you to notice that we're looking down the plane of the carbon-carbon bond pretty much in each of these cases. And the way we look down that particular bond, the way we look down carbon-carbon bonds here, straight on, where the front carbon eclipses the back carbon in both of these cases, is going to be very important. And what we do is represent this sort of view where we have a carbon in the front and a carbon in the back, and we're viewing it directly along that sort of line. We represent this in what's called a Newman projection. Okay, and a Newman projection is represented by, actually the carbons of a Newman projection are represented by a circle and a dot close to the center of that circle. The dot represents the carbon that you see in the front, and the circle is going to represent the carbon that you see in the back. Okay, and then what we do is draw in the hydrogens. So we would put the hydrogens here in a staggered, notice this is a staggered conformation. Here's where we had the dot, the carbon in the front, and we have 1, 2, 3 bonds, right? This is a CH3 in the front. And then this big circle represents the carbon in the back. It's also a CH3, and we have a CH bond up, angling down, and angling down. Those are all in the back. So the circle represents the carbon and these substituents here that are attached to it. In front here, we have the carbon and the 3 substituents, in this case hydrogens, or whatever we want to fill in. And we see that there is a staggered conformation here. Okay, how do we know there's 60-degree angle, dihedral angle between these bonds? Okay, so if we're talking about ethane, which we are, we just fill in hydrogens. And we have our completed Newman projection. Again, to summarize, Newman projection is when you take your molecular models or ball and stick model, etc., and look straight down the carbon-carbon bond. Look straight down there, and what you see is represented by this Newman projection. Okay, so for ethane, the dihedral angle we can see in the Newman projection in the staggered conformation is 60 degrees, and in the eclipsed it is 0 degrees. All right, and you can see clearly now as we've drawn these two carbons sort of angling away and exaggerated, so you can see them here clearly. You can see now the front carbon, this carbon represented here, and the circle represents the back carbon and the hydrogens. And you can see all the CH bonds are eclipsing each other. And here 60 degrees between these two CH bonds, and all the CH bonds on both carbons. So the staggered in eclipse conformations of ethane are interconverting at room temperature. So in other words, there's rotation about carbon-carbon single bonds. It's pretty easy. Now, it's very important to realize that that doesn't happen when you have a carbon-carbon double bond or carbon-carbon triple bond. So if you have a pi system, carbon-carbon bonds where you have an sp or sp2 carbon, you're not going to get free rotation. You only can get free rotation about carbon-carbon single bonds. Okay, now why would the staggered conformation be more stable or lower in energy than the eclipse conformation? Well, there are a couple of reasons. The main one is that last we checked, there are 2 electrons in a covalent bond, right? And that's going to be pretty much true for each bond that we're going to see for the rest of our lives, most likely. And so what happens is, as you have electrons in the bonds, they have, you can think of it as a partial negative character, and we get sort of an electronic repulsion the closer the electrons in the bonds are to each other. And so in the eclipse conformation, the electrons in the CH bonds are actually closer to each other, and there's more repulsion between them. Whereas in the staggered, they're bisecting this bond, the CH bond bisects these 2. And so the electronic repulsion is minimized relative to the eclipsed conformation. Okay, so the electrons in the CH bonds are going to repel each other, and that's less of an effect when you have the staggered conformation versus the eclipsed conformation. I hope that's pretty obvious. Okay, so another concept that we need to know about is torsional energy and torsional strain. So we see that there is a difference in stabilities and in energy, and it's about 3 kilocalories per mole, and interconverting from a staggered or lower energy conformation of ethane to the eclipsed. That energy difference between staggered and eclipsed conformation is called torsional energy. Torsional strain is an increase in energy caused by the eclipsing interactions. So we define what happens when the CH bonds all eclipse each other by saying we've introduced torsional strain. Okay, and that energy then, 3 kcals per mole, is for each eclipsed CH bond, since there are 3 of them, each, we believe, contributes 1 kcal per mole. All right, so let's go up 1 more carbon in complexity from ethane and go to propane. Let's go back. Let's go to propane and consider rotation about just this carbon-carbon bond. Of course, there's other ones rotating, not all the bonds are rotating, but we're just going to look at this carbon-carbon bond. Let's draw a Newman projection in the staggered and eclipsed conformations, and you should be able to do this. Okay, this is important. Staggered and eclipsed conformations of propane using Newman projections. So you can use these molecular models and see what they look like really in space. And the way we represent it is, here is our front carbon with 3 CH bonds, and you can see that corresponds to right here. Okay, here's our CH3. Corresponds to the front one, just like before. And in the back carbon, it's represented again by this circle, and notice the methyl group is sticking straight up opposite this front CH, and that's represented simply by putting the methyl group sticking straight up on the circle, which represents the back carbon. In the eclipsed conformation, we rotate 60 degrees, right? And now we can line up all of the substituent bonds, all the CH bonds and that are here, and line up those front carbon CH bond with the back carbon-carbon bond. So now we have an eclipsing CH and carbon-carbon array here in this particular instant. But the rules for Newman projections are essentially the same. We've just added we've substituted a methyl group for a hydrogen, and that gives us propane and the Newman projections of propane. All right, let's add another carbon. Let's look at butane. And for butane, we're going to have more types of conformations than just eclipsed and staggered. Okay, so we now have, so we're going to be looking here at the central carbon-carbon bond in butane. So it's going to be 4 carbons, CH3, CH2, CH2, CH3. We're going to be looking at the CH2 to CH2 bond in the center. So that's represented here by what was a dot. We connected hydrogens to and a methyl group. There's the carbon in the back, where we have another methyl group and a couple of hydrogens. So this you can recognize, hopefully, as the staggered conformation, which it is. We have 60 degrees between the substituent bonds on the front carbon and the back carbon. Okay? But we also have the methyl groups opposite each other, or anti. So this is staggered and anti. Okay, let's rotate 60 degrees, and now we have an eclipsed interaction. Rotate another 60 degrees, and you can do this very easily with, and should do this, not just could, but you will do this with your molecular model kits. And we get another staggered conformation. This conformation, where the methyl groups aren't directly across, but 60 degrees, the carbon methyl back and carbon methyl front, bond angles 60 degrees, that's called the gauche conformation. That's a French word, by the way. Okay, so that's the gauche staggered conformation. And let's keep going. Let's rotate another 60 degrees, and we have a fully eclipsed conformation. Look at that. Now we've got the carbon-carbon bonds in the front and back eclipsing each other. And this is kind of like a total eclipse, right? And then we rotate another 60 degrees, and we have the same staggered gauche conformation that we had here in number 3. And then let's go to number 6. Rotate another 60 degrees, and we have another eclipse conformation that looks a lot like the eclipse conformation in number 2. And then we can rotate another 60 and start over, and just keep rotating around and round and round. And that's actually what happens in nature, but we're considering these more extreme conformations and looking, we're going to look at the energies of these. And what I want you to think about before we go on is which of these are going to be lower energy and which conformations are going to be of higher energy. And we know from what we saw before, the staggered are generally of lower energy than the eclipsed conformations because of the electron pair repulsion minimization when we have those bonds at 60 degrees rather than at 0 degrees. All right, so to recap, 2 methyls, opposite sides, that's the anti-conformation. Methyls that are carbon methyl bonds where you have 60 degrees apart, or the gauche conformation, just like we saw. We're starting to get bigger substituents here now, so that adds some steric strain. And some, there's some steric interactions here. And so the gauche conformation, where we have gauche methyl groups or gauche alkyl substituents, is going to be a higher energy than the anti-conformation, where these carbon-carbon bonds are on totally opposite sides from each other, and there is no steric interaction between them. Okay, so staggered, lower in energy than eclipsed, right? And this is a staggered, right? And this is anti. We're not showing the eclipsed on this slide. Okay. So, relative energies of the individual staggered conformations depends on sterics. Think about that. Look at the last slide. What is going on there is that if you have a substituent, if the substituent's bigger than hydrogen, for instance, if it's methyl, you're now going to at 60 degrees are having gauche methyl groups, going to have more of an interaction, more steric strain and higher energy than when those methyl groups are anti to each other. Okay, so it's staggered anti versus staggered gauche. Staggered gauche, higher energy, more sterics. Steric strain is the increase in energy when non-bonded atoms get too close. They're forced too close. And gauche, generally going to be higher in energy because of the sterics. All right, so here is here is the highest energy conformation, where you have now an eclipsed conformation in butane. Okay, we're looking at this from the side, not head on as we had been. And that's to show you that now you have these bigger methyl groups, bigger relative to hydrogen, that is, and these carbon-carbon bonds. And you can see that when we have them eclipsed, and on the same side we have a pretty large amount of steric strain. They're as close as we can get them, and so take a look. Let's take a look then at the different energies involved and the differences in and look at dihedral angles. Notice that all we're doing here is rotating about the central carbon-carbon bond, that is the CH2-CH2 bond, represented in the front and back. We're rotating by 60 degrees. So we can start out with the staggered anti-conformation. That's going to be that's going to have the lowest energy, and then we're going to go up to the eclipsed gauche, and that's higher energy again, because now we have some torsional strain here, right? And then we're going to go rotate this again. We go back from eclipsed to staggered, and we now have a gauche methyl interaction. So that's going to be number 3 here is going to be of higher energy than number 1, where the methyl groups are farther apart. So we have more steric strain here because we have the methyl groups closer together, forced closer together. So 3 is higher than 1, but 3 is not as bad in energy, that is as high in energy as 2, because 2 is still eclipsed. And so let's go up now, let's rotate another 60 degrees about the central carbon-carbon bond, and we get the fully eclipsed, I call it fully eclipsed because now we have the methyls, actually the carbon-methyl bonds eclipsing each other. So this is going to be the highest energy, where we've now introduced this extra steric strain, the greatest possible amount of steric strain that we could have, and that's the energy maximum. So the molecule is of its highest energy in that conformation. Rotate 60 degrees, we get 5, which is the same as 3. Another 60 degrees, we get 6, which is similar, if you will, same as 2. And we'll go back to the beginning again, where we get 1, which, guess what? Last I checked, 1's the same as 1. All right, so hopefully you've seen all these extreme conformations. Remember that the molecule's rotating. There are an infinite number of conformations. We're just stopping at the eclipsed and staggered positions. And when you have substituents like methyl groups or other alkyl groups, and not just hydrogens attached to the carbons we're looking at in the Newman projection, that is the front and back carbons, we have other steric type effects that come into play. Okay, so here's a summary of some interactions and the amount of energy that they're worth. I don't want you to memorize these numbers, okay? Please don't. What I want you to do are understand relative trends and have these trends make sense to you. So let's see if they do. When 2 hydrogens eclipse each other, that is a carbon-hydrogen bond and a carbon-hydrogen bond on the front and the back carbon eclipse each other, as we've seen, that leads to an increase in energy of 4 kilojoules or 1 kcal per mole, as we said before, for each of those. When you have ethane 2CH3s, or you can multiply that by 3. But we're just looking at individual interactions now. one-on-one interaction. So CH eclipsing a CH3, well, CH3 is a little bigger, right? So the energy involved in the eclipsing here, it's a little larger. Okay, and then when we get two CH3s, two big groups eclipsing each other, we go even farther up, almost double in energy. Okay, so the greater the energy, remember, the greater the energy, the less stable the molecule is. Okay, so these eclipsing steric interactions are destabilizing interactions, right? And the gauche methyl should be of less energy, obviously, than the eclipsing methyls, and we see that it is. We actually go back when the methyl groups, that is the carbon bonds in carbon methyl groups in the front and back carbons, that when they are at 60 degrees, right? Carbon methyl front, carbon methyl back, when those bonds are at 60 degrees to each other, we go back to about the same energy value as just a hydrogen-hydrogen eclipsing interaction. Okay, so this eclipsing methyl interaction is pretty big. It's an extreme. When methyls gauche to each other, the steric interaction, not so bad. Not even as bad as a hydrogen methyl eclipsing interaction. So what we call these energy differences are between the highest and lowest energy conformations. That's what we call the barrier to rotation. When you think about that, that term should make sense. The highest gap in energy from lowest to highest, that's your barrier to fully rotating around that bond. So since the lowest energy conformation of alkanes has all the bonds staggered and all the large groups anti, alkanes are often drawn in zigzag skeletal structures to indicate this. And from now on, this is mainly how we will all draw organic compounds, using these zigzags. Now, the zigzag arrangement keeps all the carbons staggered and anti. Notice I didn't put the hydrogens in. And what you're going to have to do is assume that when you don't see a substituent on each of these carbons, that's what each of these points represent that are connected in this zigzag fashion. You have to assume that they're attached to 3 hydrogens on the end and 2 hydrogens for all of these central carbons. All right, so that's going to be it for this lecture, and we'll see you all next time.